Welcome to my video, Limit of a Function and the Derivative. In the last video I kind of talked a little bit about briefly the limit and is related to the rate of change. Now I want to give you a little more formal definition. It's not a completely mathematical rigorous definition, but it does give you the conceptual idea of a limit, which is important. So as x approaches a, that's a point on f of a, the limit of f of a is written L. So the way we would write this is the limit is x approaches a for the function f of x is equal to L. If all values of x of f are close to L for values of x that are sufficiently close but not necessarily equal to a, the limit L, if it exists, must be a unique real number. So what this is telling us is we have a graph of the function f of x, and as we get arbitrarily close to it, if it has a limit, it's going to go to this some number. But if it doesn't have one, that's going to be undefined. So limits allow us to handle motion and change at a single instant. And so that's why this is important. And the derivative in all calculus rests on this idea of a limit. So it's important we have some idea of what this limit is all about. So let's derive next I want to go and derive the derivative, or give you an idea of how the derivative comes out of this. So let's look at generally a function here. There's x, f of x, and here's going to be our line. Now if we want to draw a tangent line at this point right there, and we'll call that point x, and then over here it's going to be f of x evaluated at that point. And a tangent line just touches the graph at that point. So there's our tangent line right there. So what we know, we know the slope of the tangent line and that's going to be at point x and f of x. We know that the slope m is going to be the limit as h goes to 0 of f of x plus h minus f of x divided by h. So as we get close to this point, coming at it from the left and the right, we're going to approach whatever that number is right there. So that's kind of what that's telling us. So the limit is the instantaneous rate of change. So from this we can define the derivative. So with this we're going to do a definition. So for the function so y is equal to f of x, and we're going to define its derivative at x is f prime of x. So let's write that as a formula here. So f prime of x is going to be equal to the limit as h goes to 0 of this f of x plus h minus f of x divided by h. And so this basically is just going to be our slope of the tangent line. So if f prime of x exists, it may not exist. There may be a point of discontinuity. So then we know that f is differentiable at x. So there's our basic definition of the derivative written in terms of the limit. It's a very general definition. So now let's do some examples. So let's look at the function f of x is equal to x squared. Let's plot that first of all. That's just going to be a parabolic function. It's 1, 2, minus 1, minus 2. There's our x. There's our f of x. So it's going to go to 4 at 2. And this is an even function, so it's symmetrical about the y-axis. So there's our function. Now let's look at our definition. F prime of x, we just saw as the limit as h goes to 0 of f at x plus h minus f of x divided by h, which is going to be equal to the limit as h goes to 0. Now if we substitute in for f of x this f squared right here, we're going to get x plus h quantity squared minus x squared over h, which is going to be, expanding that all out, that's x squared plus 2xh plus h squared minus x squared over h. I just expanded all this out. Now we can get rid of some of the terms, so the x squared goes away. And so what we're going to be left with is 2xh plus h squared over h. Now our h's are going to go away, or part of them are going to go away. So what we're going to be left with is f prime of the derivative is 2x plus h. Didn't write that very well. 2x plus h. So in the limit as h goes to 0, we're going to get 2x plus h. That's just going to go to 2x. So now let's plot this. Now we're going to plot our derivative. So it's just going to be, so at 2x, at x equal to 0, it is 0. So minus 2 plus 2. Now at 1, it's going to be equal to 2. At 2, it's equal to 4. At minus 1, it's minus 2. And at minus 2, it's minus 4. So this is just going to be a straight line. So the rate of change is just constant in the parabola. You see it doesn't change no matter where you're at on the curve, and that's what that tells us. It's related to this 2x. I'm going to do one more example. So let's look at f of x plus h minus f of x over h. In this case, our f of x is equal to 3x minus 4. Substituting that in there, that's 3 of x plus h minus 4 minus 3x minus 4 divided by h. Now some things are going to fall out. Well, first of all, let's expand this even further. That's 3x plus 3h minus 4 minus 3x plus 4 divided by h. Let's see what falls out. So that falls out, that cancels itself, that cancels out, that cancels out. So what we're going to be left with is 3h over h, which is just equal to 3. But we've got to caveat that with h cannot be equal to 0 because this thing would blow up. So it's going to be just a constant. And that makes sense because in general, for a line, so what we're talking about here, y is equal to mx plus b, the derivative of, the derivative f prime of x is just going to be equal to the slope. So let's plot our function, original function here. I'm plotting this. So at x equal to 0, it's minus 4. 1, 2, 3, 4. Now at 1, it's going to be 3 minus 4, which is minus 1. At 2, it's going to be 6 minus 4, which is 2. So it looks like it's going to be a line, and that makes sense, since that is the equation of a line. That is our equation of a line, so we get a line, and the rate of change of a line is just going to be the slope m. Well, I hope you got something out of this definition of the limit and seeing how the derivative is derived from that limit and doing a couple of examples. I want to thank you for watching.